In our previous video, we talked about the derivative and average rate of change, with our last example leading us into the instantaneous rate of change, or the instantaneous velocity. We're going to continue that here with the definition. So the for y equals f of x, the instantaneous rate of change at x equals a is the limit, as we found above, as h approaches 0 of that same function f of a plus h minus f of a over h, as h approaches 0, but we never really let it equal 0, so that's why we can do that. Let's look at the difference between average rate of change and instantaneous rate of change. When we talk about them, we talk about the difference between a secant line and a tangent line. If you had geometry years ago, you may have known that a secant line was a line that cuts through the circle twice. There were 2 points of intersection, whereas the tangent line was a line that just skimmed the circle and touched it in one point. We continue that definition as we look at it as for a function. The secant line represents really the average rate of change from one point to another. The slope of that is the average rate of change. Now, the slope of the tangent line really represents the instantaneous rate of change that we're talking about. Let's develop that with this graph here. We have, it asks us in part A for the graph of y equals x squared, which is graphed above, to find the slope of the secant line for our a equals 1 and h equals 2 and h equals 1. So a equals 1 means we're starting at 1. When h is 2, we're adding 2. Recall the definition from above here. It says you're adding h to the 1. In this case, a is 1 and h is 2 and 1. So if a is 1, then a plus h is going to be 1 initially plus 2, so 3. So the slope of the secant line would be from f of 1 to f of 3. And we'll do it this way. So this is when h is 2. If we calculate this, we can get it straight from the graph. F of 3 is the y value of 3, which we see here to be 9. And f of 1 is the y value of 1, which we see here to be 1, over 3 minus 1. In this case, we're going to get 8 over 2, or 4. And that would be units per unit of time. Now when we do it when h is 1, if a is still 1 and h is 1, then a plus h is 2. So finding our average rate of change would be f of 2 minus f of 1 over 2 minus 1. You could plug the 2 into the graph and get 4, but you can also just look here to find the y value. So we'll get 4 minus 1, again, over 2 minus 1, gives us 3 over 1, or 3. Let's look at that as it is on the graph here. I'm going to increase the size of this graph and take a closer look at it. So here it's saying that the average rate of change from 1 to 3, that green line would have a slope of 4. And if we interpret that on the graph, it looks like we are going up 4 units and over 1 unit to get that slope. That's what we found here, the average rate of change. If we look at when h is 1 and we're going from 1 to 2, indeed it looks like our slope is 3. We're going up 3 and over 1. So that's why I'll get these values. Let's continue. Identify the slope of the secant line for a equals 1 and h being any non-zero number. Okay, so that is your instantaneous rate of change. Well, it's your average rate of change. So we're going to take f of a plus h minus f of a over a plus h minus a, which we discovered we can simplify to just h. So a plus h, in this case, our a is 1. So we're going to write f of 1 plus h minus f of 1 over just the h. But f of 1 plus h, we have to plug this into our function. Recall our function is f of x equals x squared. So we're going to substitute the 1 plus h into the x squared function and subtract f of 1, put that over h. As we did in our previous video, we have to square this. So we don't get 1 squared plus h squared, we have to FOIL it. If you multiply that out, you're going to get 1 plus 2h plus h squared when you simplify it. So this part right here will equal 1 plus 2h plus h squared. From that, we'll subtract f of 1, which is just, if we substitute a 1 in, we get 1 squared. And then that is over h. Then you will simplify this, cleaning it up, the 1's will cancel. And you'll have 2h plus h squared h. You will notice you have an h in each term that you can factor out. Just factor an h out of each of these. If you distributed, you get the same thing. And now the h's can cancel, and our answer is 2 plus h. And that would be the slope of the secant line for any h. And then once again, we want to find the limit as that goes to 0, which will give us our instantaneous rate of change. So the limit as h approaches 0 of our answer above is going to be 2. What is the interpretation? This is the instantaneous rate of change either instantaneous rate of change at a equals 1. All right, let's see where that leads us. As we found in our previous 2 examples, what we have when we have the instantaneous rate of change is really the slope of the graph, the slope of the tangent line. Slope of the tangent line at a f of a for this function. So it's the limit, as we had above, as h approaches 0 of the f of a plus h minus the f of a over h, where h cannot equal 0. Provided the limit exists. So in this case, the tangent line to the graph is the line through the point there, with the slope from above. Now, what is all of this leading to? Well, it's leading us to the definition of derivative. Essentially, the slope of the tangent line is the derivative. So if y equals f of x, we define the derivative of f at x. Denoted by f prime of x, like that, by the same thing. As not h, but h approaches 0. F of x plus h minus f of x over h. H doesn't equal 0. Now, notice here we use x because in this case we're talking about really the function as a derivative, not just numbers, some number a. So this would be the general case, talking about any value of x. So if f prime of x exists for each x in the open interval a, b, then f is said to be differentiable over a, b. So in summary, interpretations of the derivative, we looked at a bunch of them, but let's spell them out here. First interpretation of the derivative is that it's the slope of the tangent line. At x equals a. It's also the instantaneous rate of change and it can also be interpreted as the velocity. All right, in our next video, we will look at some examples.